One of the most deceptively obvious questions in machine learning is, are more models better than fewer models? The science that answers this question is called model ensembling. Model ensembling asks how to construct aggregations of models that improve test accuracy while reducing the costs associated with storing, training, and getting inference from multiple models. We'll explore a popular ensembling method applied to decision trees: random forests. In order to illustrate random forests, let's take an example. Imagine we're trying to predict what caused a wildfire given its size, location, and date. The basic building blocks of the random forest model are decision trees. So if you want to learn how they work, I recommend checking out our previous video linked here. As a quick refresher, decision trees perform the task of classification or regression by recursively asking simple true or false questions that split the data into the purest possible subgroups. Now back to random forests. In this method of ensembling, we train a bunch of decision trees, hence the name forest, and then take a vote among the different trees. One tree, one vote. In the case of classification, each tree spits out a class prediction, and then the class with the most votes becomes the output of the random forest. In the case of regression, a simple average of each individual tree's prediction becomes the output of the random forest. The key idea behind random forests is that there's wisdom in crowds. Insight drawn from a large group of models is likely to be more accurate than the prediction from any one model alone. Sounds simple enough, right? Sure, but why does this even work? What if all of our models learn the exact same thing and vote for the same answer? Isn't that equivalent to just having one model make the prediction? Yes, but there's a way to fix that. First, we need to define a word that will help explain. Uncorrelatedness. We need our decision trees to be different from each other. We want them to disagree on what the splits are and what the predictions are. Uncorrelatedness is important for random forests. A large group of uncorrelated trees working together in an ensemble will outperform any of the constituent trees. In other words, the forest is shielded from the errors of individual trees. So how do we ensure our trees are uncorrelated? There are a few different methods to do this. As you learn these methods, try and see if you understand what makes a random forest random. The first method to ensure uncorrelatedness is called bootstrapping. Bootstrapping is creating smaller datasets out of our training dataset through sampling. Now, with normal decision trees, we feed the entire training dataset to the tree and allow it to generate its prediction. However, with bootstrapping, we allow each tree to randomly sample a subset of the training data with replacement, resulting in different trees. When we allow replacement, some observations may be repeated in the sample. In our dataset, we have 1.88 million wildfires, but we're only going to show, say, a random 25% subset of those to each of our trees. As a result, these two trees sampled from the same dataset, but ended up with two very different training sets. Using bootstrapping to create uncorrelated models, and then aggregating their results, is called bootstrap aggregating, or bagging for short. The second way to introduce variation in our trees is by shuffling which features each tree can split on. This method is called feature randomness. Remember, with basic decision trees, when it's time to split the data on a node, the tree considers each possible feature and picks the one that leads to the purest subgroups. However, with random forests, we limit the number of features that each tree can even consider splitting on. For example, consider the two trees shown here. The first one only sees the location and size of the wildfire, while the second one only sees size and date. As a result, the two trees learn very different splits. Feature randomness encourages diverse trees. Because the individual trees are very simple, and they're only trained on a subset of the training data and feature set, training time is very low, so we can afford to train thousands of trees. Random forests are widely used in academia and industry. Now that you understand the concept, you're almost ready to implement a random forest model to use with your own projects. Stay tuned to Econoscent for the random forest coding tutorial and for a new video on yet another ensembling method, gradient boosted trees.